Alright, let's assume that we already have diagram, which is very easy to do. And then we open the pre-processing and look for the work directory, work dir. So you should be in the Chemkin folder. If you move to other folder, it's not gonna work. It's gonna have some error. And so I said the best way we should stick with the folder inside the Chemkin. Let's say that. So after you give a new folder, just select it, and then for the chemistry set, go for the new chemistry set and give the name. I'm gonna give my name on it and the date today, and then you have to add for the inp file, which is the file. This file I got it from Hadi. It's the file that tell you the mechanism. So you can add whether it's a text or .inp. In this case, you have to select for all file and select the mechanism and then open. And then you select the thermodynamic data file, which is about the same thing. In this case, the file is in the txt format. And then you add the the transportation file and save as, and just save it right away. I'm not gonna give it any new name. And then you click the run preprocessor and wait for a few seconds. When it's ready, you're gonna see something inside the mechanism viewer. You're gonna see a lot of mechanism inside. Alright, when we take a look at the mechanism viewer, you can see thermodynamic data, transport data, gas phase reaction, and whatsoever, so on and so on. You can see the number ABE is the number that's corresponding to the file, the txt file that I got from Hadi, and this is included all the mechanism. In this case, we're gonna have the mechanism for just hydrogen, nitrogen, and oxygen, HNO. So if you want to do something other than this, like you have like a hydrocarbon, that's a no-go for this one. Alright, this is a file that I got from Hadi, the mechanism file, thermodynamic and transport. Let's come back at the program, the software. This is the mechanism that we're talking about. Well, what you can do, you can check out for the ABE term is a coefficient that you got. People say that you got from the mechanism file. When you take a look inside, see the number 7.000 powered by 17. You see that? Anyway, that's one come from experiment, come from the calculation, and maybe reduced by the previous researcher, which is in this case I took it from Dr. Hadi. Well, I tried to take a look, but it doesn't make any sense anyway. Alright, let's come back to the software. Go back to your project. Now we are going to set up for the frame speed C1. Let's go for the frame speed. Alright, double click, and then there's a setting. That will be some description later, some explanation from Dr. Hadi. Alright, I'm ready.
Okay.
Frame speed.
So we are okay. As I said, you can choose to include the sword effect, which is a thermal diffusion effect that kind of predicts more precisely based on thermal diffusion of each species.
But we can skip it.
You can skip it, but in future, if you want to be more precise, you can choose that.
Alright.
So, and all you have to do is you give the initial temperature of your mixture.
Let's say about
400 degrees Celsius. So
that would be 673.
Okay.
Kelvin.
Kelvin.
Alright.
An automatic estimated temperature profile, which means that in each iteration it's gonna estimate your temperature profile, unless you have your user-defined temperature profile, which we don't have. That we don't need that.
Just let it.
Yeah, we let it solve itself. So,
okay.
And your pressure, you have to define your pressure, atmospheric maybe, huh?
1.
Yeah, 1. So we don't need, and these are usually the default. I mean, ambient temperature you can
25 degree.
Yes, you can change that, but just example. That's all you have. We don't have to define anything else here. For example, minimum for product estimates. These are all details if you want to add, but we don't need that. Basically. So. Then this is done, we can go to the grid properties. Now you should imagine a one-dimensional, it's a one-dimensional solver now, okay? So your mixtures enter from the
More like a, like this.
Exactly, it's a tube. Your mixtures go here. And this is your reactor.
Length.
And it comes out of that.
Like that.
So this is length of your reactor. You can choose it, for example, the length, how many centimeters is that? Starting axial position, ending axial position.
So we should
let's say for example, let's say for example it's 2 cent.
2 centimeters?
Yeah.
Just that, okay.
You can, depending on your real situation, you can define that. But
can I go for something like 10 centimeter?
Yeah, why not? Let's go 10 centimeter.
Make more sense.
So, but for 10 centimeter, this is a key factor. How much number of grid points you are giving for that 10 centimeters. If it's very less, your estimations, your
rough
will be very deviated and not correct. If it's very high, it will take so long. So this is on practice. For example, for 10 centimeters, you can give 500 to 1,000 as my experience.
Okay.
So let's say, for example, 1,000.
1,000.
Yeah, 1,000 grid points. So it kind of, you know the
1,000
how it works. 1,000
divided
nodes. Yeah. So at each node it solves.
It's gonna look like this.
Yeah. At each node, at each grid point, it's gonna solve all the reactions. To estimate the species concentrations, laminar flame speed, and all. Okay. So that's done.
Okay.
That's okay. I mean, this is the start point.
Adaptive grid point. What is
this
that?
if you wanna change your grid type.
Yeah.
When you say this is my 10 centimeter reactor, and distribute 1,000 points on that, it does that on the same intervals, like 10. Over 1,000, how much is that? I mean, for each
1,800.
Okay, it means
0.01.
Yeah, that's your grid intervals, grid length, right?
Okay.
I mean, it does that uniformly.
So in this case, you're gonna have the interval of 100 intervals.
Yeah.
In overall.
Or for example, if you want to make this part entrance very very fine grid. Yeah. And here it's not important to you, so you can make it very coarse grid.
Like
this. Exactly. So you can
like this.
Yeah. So you can define here, but you don't need that. I
always
make
go it uniform.
Uniform works very good. Now let's go with species properties. Okay.
Immediate fraction.
Do you have any intermediate fractions?
I have no idea.
We have no idea because we don't know what. I mean, depending on conditions, you can have different intermediate fractions.
One question. Right now, we are going to do the combustion.
Yes.
Of what combustion of what gas?
We can select, for example, methane? Combustion of hydrogen. Or ammonia.
Your mechanism is like include everything in one, no? Like you can do whatever with this mechanism.
Not carbons, carbon-free fuels. It's
carbon-free.
Yeah, NHO mechanism. So you can have mixture of any fuels as your input fuel. For example, you can have 20% hydrogen.
Yeah.
80% ammonia as your fuel and air as your oxidizer.
Okay.
Or you can have pure hydrogen, pure ammonia.
So shall we test with hydrogen, oxygen, the easiest
Yes,
one?
yes.
So
let's go with product.
Product fraction.
If no product fraction is specified, the model will use equilibrium calculations. Okay, so it depends on you. If you say, I'm sure that I have these products at the end.
Yeah.
It's okay. It will adapt the solution based on that. If you don't know what comes out of your reactor, you just make it blank.
Just leave it.
Leave it.
So let's leave it.
Let's leave
Shall
it.
we?
Okay.
So, do we have to set up anything in intermediate
Again,
fraction?
if you have very strict boundary conditions, you say, okay, I know in this reactor these species will produce and will be abundant, so you can define here. If you have no idea, that usually we have no idea because it's combustion and I don't know about the conditions, what happens. Leave it.
So basically,
so that's done.
Grid properties, this, that, double check.
Okay, it's done. Let's go to inlet.
Inlet. Please remember to provide species composition data.
So this is an estimation that you have. This inlet velocity, it will iterate, the solver will iterate and find the correct number for that. So you don't have to worry about that. You just estimate the flame speed.
This is a flame speed.
Yeah, because inlet velocity will be balanced with flame speed, right? Your flame will be here, okay? This is your flame, okay? This is your unburned.
We try to go to the flame front, go to the unburned part.
It goes here, but your velocity will keep it in the middle. So this flame speed equals the velocity.
It will do automatically?
Yes.
Okay.
I mean, this kind of reactor is based on you have combustion here, so you have to hold flame in the reactor. So this is kind of estimation for the first iteration of what your velocity is. It's based on the velocity of your flame.
So 40 centimeter per second is alright.
40, 10, it depends. You can if you can't get proper results or it fails to converge, you can change this number.
So try and error until you get this number.
But what I usually do is instead of inlet velocity, I define mass flow rate.
Okay.
Because that's more realistic. I know how much mass flow rate I have.
Yes.
For example, we can say I have 1 grams per centimeters second.
Gram per area?
Gram per area, for example, this mass flux that you have from here, right? This is the unit area. Look from this side.
Okay.
This is the unit area.
The cross-sectional area.
Yeah.
Okay.
So this is kind of the standard area that you have.
Okay.
You can say in 1 second I give 1 grams of fuel or inlet.
So how much we should go for now?
I usually go with 1 or 2. Then I see the results. If it fails to
produce the result, then we change it again.
Yeah, we can change it.
Okay.
Or if you're more comfortable with velocity, go with that. That's okay.
I would comfortable with mass flow
me
rate.
too. Okay. So let's go to the species.
Okay.
What do you want to define? You know equivalence ratio? We usually know.
It's phi, right?
Yeah.
Okay.
We usually know we are gonna burn rich or lean or stoichiometric.
Let's say stoichiometric.
Yeah.
So
okay. So
go with 1.
Go with 1.
Right.
Exactly. So now it says you have to define your fuel mixture. What are your fuels?
Okay.
So fuel fraction. This is mole fraction or mass fraction. Depends on you.
Let's do mole fraction.
Okay. So what do you have in your fuel?
Hydrogen?
If it's just hydrogen, so it's mole fraction. So this should be 1, right?
1 mole.
1 mole. It's fraction. If you have 4 different species of fuel, the summation would be 1.
So I have to write.
Yeah.
So I have to write like a equation for the.
No. You don't have to write. You say.
But you have to know the mole
Yeah,
fraction.
It's for example, in your experiments, you want to give 20% hydrogen and 30% ammonia, and for example, as a fuel, what else? Just let's say 80% ammonia as your fuel mixture. Okay.
Okay.
So if it's volumetric, give it 0.2, 0.8.
Okay.
If it's mass based, you can convert this to mass based 0.2, 0.8.
Okay. Right? Because this is just fuel, so my fuel just hydrogen, and my oxidizer will become oxygen. The oxidizer will fill
exactly.
in this.
We don't care about oxidizer now. We know that the summation would be 1.
One fuel. Okay. So that's the data is mean the fraction number.
Yeah.
Got it.
Okay, add it.
Add it.
So this is your fuel here.
Yeah.
Let's go to the oxidizer.
Oxidizer. Okay. If I want to use oxygen, go for oxygen. No.
Let's, for example, use air. That's
air.
Oh, for air, mole fraction is usually what? It's like
21,
79.
79.
Okay.
So I should oxygen 21.
Yeah. 0.21.
Oh yeah.
Okay.
And N2 will be 0.79.
You know, when you're choosing this, it gives you all the species in your mechanism, right? So this is the power of the mechanism you have introduced. Now you can choose any species with all the thermodynamical and transport properties that we have given to the system.
The
right?
phi that we introduced.
It doesn't randomly get oxygen with its default properties, right? It's the properties that we have defined. So that's the.
So it's like it's fixed the possible choice for you.
Yeah.
That's at.
Okay.
Okay.
This is all our fuel and oxidizer. What would be a complete combustion product?
Water.
Water and nitrogen, right?
Water and nitrogen.
Yeah.
Yes.
That we know.
So you should react.
Yeah, you should.
Water, nitrogen. That's it.
That's all. So if you want to add a species, you add that. But here we don't have any specific species we want to add.
We should have like a complete combustion. We just choose species.
Yes.
So no added one.
Yeah. That's all.
So what
we
else?
Are
done.
Yeah.
And
let's go to the
solver.
Now this is important. The solver is all you should control when you can't converge a solution or when your solution is failed. So you are going to control from here, right? So what you have here is the absolute tolerance. It means that when your iteration number n plus 1, this is the number of, for example, it's going to iterate for you depending on your result many times, right? Iteration number 1, 2, 3. Let's say you have iteration n plus 1, n plus 2. If your iteration number n plus 1, the difference on, for example, flame speed. Here it says that your flame speed is 2 centimeters per second. And here it says it's 2.00001. It means that your solution is converged and you solve the problem. It will give you results. It will continue the iteration until this relative tolerance is met. So until your solution here, difference with this solution is this much.
At least.
So if you are looking for a very precise solution, very, very, very precise, you can reduce this number, 0.0000001.
Smaller number.
It will take forever, or it will take 1 hour more for you to solve this problem.
Okay, so
I usually make that default because it's a good number in terms of what we are doing, like flame speed, concentrations, NOx. So I don't really change this one, but let's go to the advanced one. Here it's very important. It says that number of time steps and initial size of time step. So this is very important in the sense that sometime you fix your problem, you give all the conditions, temperature, pressure, everything, but you see that you start to run and it fails just immediately. It means that your initial time step is not
enough.
Exactly.
Too short.
It's too short.
Okay.
Too large. Sorry. It's too large.
Too long.
Too long. Your time that you are given for one time step is too long.
Oh.
Okay. So you have to refine that time step. For example, in the first iteration, what's your time step? If it's like 10 to minus 6,
1 microsecond.
so it will do like this. If it's 10 to minus 10, it will resolve like this. Okay? This is more probable to give you the answer. Am I right?
Yeah, because it's too long, it's like spread.
Yeah. So this, if it's too long like this, it means that it can skip some of the time scales of the reactions. Some reaction steps have very, very short time scale.
Happen.
Yeah, to happen.
When you give it too long, it's gonna go wrong.
It will skip that, and it can convert, and it can diverge.
Okay.
Right?
So how do we know that? What is
By practice, by experience.
Okay.
So you can, for example, for this case, this is your default. You can keep it like this.
Okay.
If it diverges, what we are going to do is we are going to decrease this to 10 to minus 7. Okay?
10 times.
Yeah. Then initial size of your time step for pseudo time steps, again, decreases 10 to minus 7. And you see minimum pseudo time step. There is a minimum for this.
Okay.
You can also decrease this one. I can say refine this time step until 10 to minus 20.
20?
Yeah.
Okay.
It depends on you. Okay? So this is what I do. It diverges. I come here. This is 10. I make it 10 to minus 7. 10 to minus 7. 10 to minus 12.
Should I change it now?
No, we haven't done yet.
Okay.
So it diverges again.
Let's use the default number.
Yeah. It diverges again. I can't make it 10 to minus 8.
How can you tell whether it's diverged or not diverged?
If it can't solve, it's diverged.
If it's solved, it means it's diverged.
It's converged.
Converged.
So Chemkin is very stiff solver in the sense that if it is solved, it's converged, you know that.
Okay.
Let's go. Okay. We are done with that. We don't need to change that yet.
Yeah.
So just
For
close
now,
it. Yeah. You
keep
can
it.
close it.
Close.
Okay.
This is the inlet. Close.
We have done that. Close.
The frame speed.
Yeah, close.
Close.
Okay.
Diagram.
Output.
Output control.
You can control your output, but if you want to do a specific analysis.
Hey guys.
Hey.
Is Greenwood here?
He was here.
I think he went down to the lab.
Alright.
See you.
See ya.
So, for example, if you want to know about all the A factor sensitivities,
What is a factor?
that's, for example, you have reaction step, A plus B gives you C plus D. So you have 3 parameters, like for A, B, and activation energy. Those 3, the reaction steps that we have mechanism. Yeah. So this is your A, or pre-exponential factor. You know what this is? In Arrhenius form, for reaction rates, you know that.
Long times ago.
That's okay. So this is, for example, your A plus B gives you C plus D.
Okay,
Right.
the normal
So-
reaction.
Your reaction rate, what is your reaction rate? Let's say it is dA over dt. The rate that A is going to decompose or change, the conversion rate of A is your reaction rate. You know that this is in the form of a constant.
Okay.
Yeah, it's a constant times the concentration of A to some power times concentration of B to another power. We don't know these numbers yet, okay? This is defined by experiments, so we don't care about that. But this reaction constant K, this is very important. Arrhenius says it's in the form of this. There's a T powered by B exponential minus activation energy over RT. This is the form Arrhenius says. Always in all reaction steps, you can say the reaction constant is in this form. What's this form? This is a constant. Comes from the experiments. They say pre-exponential factor. This is dependency of pre-exponential factor on temperature. This is a very weak dependency. So
Temperature dependent.
it's usually 0 or very.
If it's 0, which means this term gonna be 1, right?
Yeah, this will be, usually it's 0. So it is in the form of A times exponential activation over this one. The major temperature dependency comes from this exponential term. I mean, when you are changing your temperature of reactor, do you know why it affects your reaction rates, everything? It's because of this term. Because of this term. You change the temperature.
Higher, which means this term overall is less.
Yeah, usually when you change this increases, right? Usually. I mean, it depends on your reaction rate.
Increase K.
Yeah, so it means that your reaction rate increases. So when you increase temperature, you increase conversion rate, usually.
Oh, that's why higher temperature, better conversion.
Yeah, most probably. I mean,
in most cases.
Most cases. Some reactions react, completely reverse. It depends on the reaction. So this is the temperature dependent term. This is your activation energy, right? So that's all the form. And when it says the A factor sensitivity, it means that if you want to study the sensitivity of this pre-exponential factor, you can choose that, and then at the results it will give you some diagrams that you can analyze. If you want to do that, there are tutorials for Chemkin. You can just study that, but I don't think you need that.
Let's make it easy.
Yeah, for now we don't deal with that.
Don't deal with it for now.
For any of them, okay.
Okay.
If you want to see the sensitivity of a species, for example, if you want to see you have NOx, okay, at your exhaust. If you want to see what happens to NOx if you increase a little bit temperature, if you increase, for example, anything.
Okay.
If you change one parameter, what happens to your NOx? If you want to study that in a very, very detailed manner, you can choose that species here. And at the end of your solution, it will give you the sensitivity path for that specific species. It will give you a sense. If you increase your temperature, what will happen to your NOx?
Output, right?
Output. If you decrease your pressure, what happens to NOx? And all those things. Okay. So this is a very professional way to see what happens to one species in terms of other parameters. Okay? I mean, you can, as I said, you can study that and use that, but for now we don't need.
We want to make it simple, so we can skip those output control and...
We don't need that.
Okay.
Okay. So close this. That's okay.
Continuation.
If you have two different reactors that you want to connect them to each other. So reactor number 2 is using the exhaust of reactor number 1, you can connect them here. But we don't need now. We just have one reactor. Okay, skip
So,
that.
for example, I have 2 of these.
Yeah.
When I want to, so I have to put number 1.
Yeah.
But in this case,
We don't need.
okay.
You can have many reactors and connect their results to each other, right?
But
We
we
can
don't.
do that. Yeah, we don't. So close this. Run calculations.
And
Begin.
begin.
Now it's running. Okay. Now it gave you the results. Next step. So now
It's done?
It's done.
Oh, why so fast?
Now here you can see all the results you want. What parameter you want to see at your results you control from here. For example, if you want to see pressure, actual velocity, everything. But what I usually do is I select all, again, clear all, and you select what you want. For example, you want laminar flame speed, NOx. You can come down.
Like this?
Yeah, from here. So, in your exhaust, you want to see how much, for example, hydrogen you have left.
Yeah.
Come down.
Nitrogen? Should
Nitrogen. Okay.
Water?
Water. And this is going to give you the concentrations, right? The concentration of NOx along your reactor. What about if you want to know what's the rate of production of this species?
Rate of production. So I click here.
Yeah, the conversion rate. So you click here. For example, conversion rate of NOx. You can see.
N2O is alright?
No, that's nitrous oxide. We don't care about it. Come down. Okay, yeah, this one.
No.
This
This and
will
this.
Yeah, also this one.
NO2.
Okay, let's keep it simple. That's enough. Let's come here.
Can I go back a bit?
No.
N2, H2, no, H2O. H2O is here. Should I go for it?
Yeah. Okay. Come here. There's a laminar flame speed in the bottom, I think. Where's that? No. Flame speed. Okay, now you have all you want and process solution data.
Okay. And
okay. Let me remember. Can you close this?
close this first.
Yeah.
Okay.
I want to make sure. Next step again.
And
I want to show them. Use Excel.
okay, so I select.
Oh, again you have to choose that.
Yeah.
Choose some random. That's okay. But don't. Yeah. And one of the ROPs, and let's see the
NOx.
flame speed and NOx. And flame speed. Okay.
Yeah.
Use Excel.
Use Excel.
I usually use Excel. That's much better.
Yes.
When it's in format of Excel, it's easier for you to plot the results. So that's there.
Okay.
Those are
Now
the
we
results.
got Excel. Wow.
So solution number 1, depending on distance of your reactor from
Then I
1.
divided by 1000.
Yeah.
Okay.
No, these are divided by the number of iterations it has, not necessarily 1000.
Not necessarily that number.
Yeah.
Oh, in this case.
But your start position would be 0, your end position would be 10 centimeters.
Yeah.
So you can see that this starts from
It starts from 0.
0 centimeter to 10.
Well, this look like a 0. Let's say 0.6, 0. And then
Yeah,
it's increased like every
you cannot
0.6.
control this. It refines automatically based on conversion rate, right? It wants to converge.
That number that's 0.0001, right? The one that you told me.
No, this is time step. This is not time step. This is your distance. This is your x portions that it has selected to solve
Yeah,
that.
is that the one that you explained me here?
No.
No, not that one.
No. You have t. This is your time.
Yeah.
That's proceeding.
Okay.
Time steps. Step number 1 to step number n. So what you say is refine this time step like this, or refine it like this, or like this.
Oh, that 10 power minus 6.
Yeah, that's this one. There's another distance or directional time steps. For example, you said my reactor is this long, from 0 to 10 centimeters.
Yeah.
And you give an initial estimation of how much fine your grid should be. You say make it 1000 grid points in here. What I mean is here you will see all your solutions from 0 to 10,
Yeah.
but not necessarily 1000 points. It resolves them based on its own solution method. Not this is just your
Not by
estimation.
how much you divide it.
This is your initial estimation. It gives that, so the initial grid will be 1000,
Yeah.
but when it goes to the second iteration, it will choose its distances itself. The solver will choose it
Does
itself.
it mean that, for example, from 0 to 1 or 2, 3, it's like in this length, even it has been divided, like maybe
Yeah,
you have
yeah.
like 10,
Yeah, yeah.
20 of them.
Yeah.
It means it has the same
Yeah.
result.
Yeah.
Okay.
So you can see your temperature here. Can you see?
Right.
Go down, you can see the temperature is changing.
It looks like it increased.
Yeah. So you can all plot that in your in any axis. Like this is your t, this is your x. You can easily plot that. You'll see there's something like this. So this is 0, this is 10. You can see that at this point of your reactor, you have the highest temperature. Okay. So what about, for example, mole fraction of
hydrogen, mole fraction, water? No.
whatever
no.
we chose? Okay.
But
So let's see what's
no
the
flame speed.
No, the flame speed will be in the other part in here.
Take a look here.
Yeah. You see your flame speed is this one.
This is the length.
No, this is the number of solution.
Number of grid.
Because we are solving one problem.
Okay, one reactor, one problem.
One problem. One conditions for one reactor.
Yeah.
We can choose different conditions at the same time, so it can solve your reactor with different initial temperatures, with different pressures. I'll show
So
you
you
that.
can put like many initial conditions,
Exactly. So it
but
will
we
be
have like
solution
just
of
one.
Yeah. 2, 3, 4, 5. So I'll show you that.
The frame speed is like, wow,
Nine.
97.
No, 9.7 centimeters per second.
But it has this. E.
Oh, yeah. Because it's hydrogen.
Oh, wait. That would be 971.
71. So at temperature, what was your temperature? 400
Yeah.
degrees Celsius. Your hydrogen flame speed is this much. This is a very correct number. Why? Because at 20 degrees Celsius, it is about 280 centimeters per second.
The higher, the faster.
Yeah, exactly.
Alright.
So let's go this one.
Rate of
These are rate of
production.
reductions. These are also very interesting because this is total. Let's go to, for example, hydrogen.
Hydrogen.
Water.
I only take out the
Okay.
water.
Let me tell you like this. These are all the reaction steps.
React steps.
So this is one reaction step, right?
Yeah.
This is one reaction. These are it shows all the important reaction steps that water is whether in this side or in this side. I mean, you see, any reaction step that you have water in the production side or in the input side, it shows you how much rate of production of water is.
How can we know where it's on which side?
You can see reaction number 8.
Number
So
7.
reaction number 8, at this distance of your reactor, it produces this much water in terms of mole per second.
Reaction number 8.
You can go see what's reaction number 8. Go to pre-process. Okay. View results. Gas phase kinetics. Yeah.
Yeah.
So what's your reaction number 8?
Oh, hold on. Okay.
Come down. Okay, these are reaction number 1, 2, 3. Go to 8.
8.
You see, it says that the rate of production of water from this reaction is that much. You see, it's very detailed. You know
that much and that certain length.
At that certain point, you are producing water with that rate.
Okay.
This is that detail.
That
you can
reaction.
do anything with this.
So,
for example, you can. What I did was always I was looking into the NOx. So, where NOx comes from, which reaction is most responsible for production of NOx, you can see from here.
So it's like, so I have to look for the highest number.
Or what you can do here is you sum all these numbers through your all from 0 to 10. You sum these rate of productions. You sum all these numbers.
Yeah.
And you can see that, okay, reaction number, for example, what's this reaction?
Number 15.
Okay, you can see that number 15 is responsible in all over your domain, is responsible for this much production.
I want to take a look, I have to go to the same one and take a look at number 15 from here.
Yeah.
15, so nitrogen plus atomic oxygen.
Yeah. And what you can do, this is a trick I'm telling you, what you can do, this is reaction number 15. For example, we are looking for NO now. You see in your Excel file you have reaction number 10, number 3, okay, 4. These are the reaction numbers that producing NO. You summarize these from 0 to 10 centimeter. Okay, you all summarize. You sum these up.
Yeah.
So here you can see this is, if you sum that,
the
it's
total
like
reaction.
Yeah. For example, 1 mole per second, 2 mole per second, 5 mole per second. What you can see from here is that reaction number 4 is very important in production of NOx.
It's the one that dominates the reaction. Yeah. So when I take a look there,
you see,
right?
Yeah. You can do this for all the columns and see which reactions are important for which.
Can I do like this?
Yeah. You can do it later. I mean, I'm just giving you some ideas what you can do with this. For example, you have ammonia as your input, as your fuel that or in your decomposition.
Yeah.
You have ammonia as your inlet. You want to see which reaction is important in decomposition of ammonia. Okay.
So actually this is the end, right?
This is the end.
So let
With this, you can do everything. You can look into everything. You can know which reaction converts ammonia the most.
okay.
With doing this.
And using your equation, I mean mechanism.
Yeah.
Because your mechanism is HNO.
Oh.
So is that enough for, I mean,
If you have
basic
carbon, it doesn't work.
Yeah, that's the thing.
But what we can do for carbon, I'll give you a detailed mechanism, the reference one.
Yeah.
So it will take a little bit longer than this because it's reduced mechanism. But still, if you put your reference mechanism
Yes.
as an input to this, as what we did for my mechanism, you can have carbon also inside. So you can have detailed, again, you can see what produces carbon dioxide, what produces carbon monoxide. You get the idea, right?
Yeah. To get the mechanism, we need that library. That's all.
I'll give you that's okay.
And for now,
So
the
now
diagram is more like for the laminar frame split.
Yeah.
But
you can do that for any kind of reactors. For example, go save this.
saved it. How?
Save.
Okay.
Just save. Okay, now you can close this.
Like this.
No, just close this.
Close it.
Okay, open a new one.
Create a new one.
Name it like.
SAP 2.
But you should name it in a way that you will have many reactors, so you can understand from the name which one is this. For example, decomposition. This reactor, for example. Okay.
Yeah.
Okay. You see, you have many reactors.
Because I want to do the ammonia decomposition.
Okay.
So which one should I go?
So you can what you can do based on your conditions.
Yes.
You can look at the tutorial, because in the tutorial there are all definitions for all these reactors. You can
Okay.
see based on your conditions and what you want to do. There is a very brief description of each reactor before it starts details.
Okay.
You can select your reactor based on that. For example, whether you have to do the plug flow reactor or
Plug.
homogeneous reactor. This homogeneous reactor, for example. This is, I think,
Flow,
plug
yeah.
flow. Yeah, I think, or this one. Look at this.
Honeycomb monolith. Yeah, that's more like it.
Okay, I mean
Plasma.
plasma. What's this?
Palana, shear flow, cylindrical.
I think plug flow. This one is good for you.
This one.
One
right?
of them. Look into their descriptions from tutorial. If it
Yeah.
fits your needs, just again you have an inlet outlet
And repeat.
and repeat. Just it will.
Can I take a look from here in the tutorial manual? Does this make any sense? What do you think? I just started just introduction yesterday because I've been reading the other one, but seems like they have like, some
Examples?
yeah.
Yeah, why not? I showed you what you can do with this, right? And
Yeah.
how you can integrate your mechanism into that. So you can do anything, or you can use any example to do your thing. It depends on you. But
Okay.
anyway, any questions you have or any problem, we can discuss together.
Yeah. When I try something
Yeah.
and I give the
Because-
results.
Because I have not used all these reactors, I have used just some of them for my purpose in my
Okay.
PhD. So most of them are also new for me, but we can learn. We can do that together.
That's cool.
But
Do
I
it.
know the errors. I know how we can fix them. I
Yeah.
know some numerical tricks.
You mind if I put it on YouTube? Usually I put my personal YouTube,
And see, we can do that.
teach people,
Yeah.
So we have one more tutorial
Yeah, why not?
from Dr. Hadi. Thank you.
You're welcome. Yeah, just continue, and I think what you should do is, you have, for example, this laminar flow. Yeah,
Mm-hmm.
that's what we did now.
Yeah.
You get their results. You plot some results. For example, plot temperature versus X. Okay, you have Excel.
Okay.
Just
yes.
plot this. Then let me show you one very interesting thing that you can do. Okay, close this.
Close.
No, not this one. Don't update. Don't want that.
Go back to the project.
Yeah.
Yeah. Okay.
Okay, which one does? Okay, it was this one. Huh? Okay, go to our flame speed. Let's say it's this. Let's change. Let's keep this open. Oh no. Okay, this is a very good thing to test. Now you want to give, at the same time, you want to solve for different temperatures to see what happens to, for example, flame speed with respect to temperature. What you can do here is this one. You see this guy. Set up parametric study. Parametric study. Set up that. Okay. You say start my temperature, let's say from 200, 473, your start temperature.
400.
For example, what I want to say is this one. So you can look what happens to the flame speed if your temperature is 200 degrees Celsius, 300 degrees Celsius,
so we
and
have
up to 700.
Set the interval.
Yeah, so choose the start from 473.
473, 200 degree, right?
Yeah.
Oops.
And go up to
maybe 1000.
600.
600
would be what? Would be 873.
Yeah.
And number of values you want here, how much would that be? 1, 2,
3,
3,
4, 5,
4.
6, 7. 7?
Is it 7? 400.
4, 5. Increased by 100 degree, right?
Yeah. Or you can say increase by.
Increment.
Increment, okay, 100.
100.
Calculate.
So, calculate. I did it by mistake yesterday.
Okay, done. Okay, now let's run the same thing.
And that's gonna be
Run.
parameter study.
Yeah.
So it's gonna take a little bit longer.
Yeah. 1, 2. Each of them is one case. 3, 4.
Yesterday I did like 1,000 cases.
So.
On the results.
Yeah.
Next step. And
No. Let it done.
let it do it.
Okay.
Okay, we generate a lot of Excel.
No,
file.
just one Excel. You see, it's very, very.
That's spooky.
Okay, look at this. Okay, at this unburnt, look at this. This is your initial temperature.
Yeah.
This is your flame speed. You can see. So you can have your flame speed with respect to temperature. You can see that it should be something like this. I mean, you can do anything you want with this.
Like
you're
playing around with the parameter.
Yeah, you can look to the effect of pressure on
So
flame speed.
I set the parameter study for the pressure.
Yeah.
Okay, cool. And why did it generate so many fire?
Because it is, for each case, it has done all the rate of productions, all the things.
And then it's merged together.
Yeah. What I do, I don't tick all these outputs. For example, if you just want to look into the NOx, just tick
thing.
NOx.
Okay. Otherwise, you're gonna get like 100 columns.
And it will be 100 megabytes.
Shit.
For example, this is not like that. But if you tick all of them,
and this is like all the cases, all the parameters study at different temperature.
Yeah.
All right.
You see? So, for example, you can see that at T equals 200 degrees Celsius, you can see that NOx production is mainly done by reaction number
15,
when you increase your temperature to 600, this is not anymore.
And it's shifted to other reaction.
The reaction number, for example, 3 would be the most responsible for NOx production. So you can have very good ideas of, in experiment, what you can do, what's happening, why, for example, NOx is dropping. You can know from here.
And we know the mechanism that is responsible for that.
Yeah. I mean, this will also help you very much in analyzing your experimental results.